Section 6.1 is about inverses. And we've had inverses show up before, but more just for numbers. So like the idea of an additive inverse, it's the number that you would add to some other number to end up with 0. So like here, if you add 5 to -5, you get 0. So these two numbers, 5 and -5, are additive inverses of each other. And then for a multiplicative inverse, if you multiply two numbers and you get 1, then those two numbers are multiplicative inverses of each other. So like here, 3/4 times 4/3, you get 1. So 3/4 and 4/3 are multiplicative inverses of each other. For functions, the way to see if you've got functions that are inverses uses composition. So it goes back to something from a little earlier this semester. And there are a couple of examples of it down here. So this is the idea. You have to do the composition in both directions. So f composed with g and g composed with f. And both times you have to end up back just with x. So with the identity function, right, where you just put x in and you get x back out. So the first example is, what if f of x was x plus 3 and g of x was x minus 3? Well, then we can do both compositions. So f composed with g of x would be f of g of x. So then I just subbed in x minus 3 for g of x, since that's what it is, right? Like it says over here. But then f of that, you would take x minus 3 and then add 3 to it, but x minus 3 plus 3 is x. All right, so that works out. And then what about in the other direction? So g composed with f, that's g of f of x. And then I subbed in x plus 3 for f of x. G of that, you'd have x plus 3, then minus 3. You get x there as well. Then a couple that involve multiplication instead of addition and subtraction. So here, you do both compositions. F of g of x ends up being f of 1/4 x. But then f of that, you would multiply it by 4. So 4 times 1/4 x, that gives you x. And then g composed with f, you go the other way. G of f of x means you'd have to multiply 1/4 by 4x, and that's also just x. So yeah, in this case, they're also going to be two functions that are inverses of each other. The last example on this page is just one that's a little bit more elaborate with the functions. So to show that 4x plus 3 and x minus 3 divided by 4 are inverses, well, we just have to do both compositions. So f composed with g of x, that would be f of g of x, but here g of x is x minus 3 over 4. So f of that, you'd have 4 times x minus 3 over 4, and then plus 3. 4 times x minus 3 over 4, you can just cancel those 4's out, and that's x minus 3. So you end up with x minus 3 plus 3. Yep, that works. You get x. That's why I got the check mark over there, because you get what you're supposed to. Then g composed with f, that's going to be g of f of x, but f of x is 4x plus 3. So we need to take that, subtract 3, and then divide by 4. But this numerator is really just 4x, right? And then 4x divided by 4, that's x. So you get what you're supposed to. That one works out as well. So when does a function have an inverse? Not every function will have an inverse. Sometimes they do, sometimes they don't. And the ones that do are functions that are one-to-one. So what a one-to-one function is, it's one where every value that's in the domain gets mapped to exactly one value in the range. Or in other words, a function is one-to-one if, I guess, either of these happen, right? These are logically equivalent. They're just in opposite directions. Or one's the contrapositive of the other. So if x1 and x2 are different, so you have different x values, if that means that f of x1 has to be different than f of x2, or the contrapositive, if f of x1 equals f of x2, then x1 equals x2. So to put it another way, a function's not going to be one-to-one if there's one instance of this, or at least one instance of this somewhere, where you have x values that are different, but then the corresponding function values are the same. The easiest example for where that would happen for something that's not one-to-one is a parabola, like y equals x squared. Because then, or f of x equals x squared, right? Because then you say, well, then f of 2 is 4, and f of negative 2 is also 4. So something like that would be a function that's not one-to-one. And if you have a one-to-one function, it's got an inverse, which itself is also a function. And if a function is not one-to-one, you could still get an inverse, but it wouldn't be a function. So basically you get something that fails the vertical line test. All right, so we got some examples here to figure out if they're one-to-one functions or not. So the easiest way to check is actually, if I go back up here, usually it's using the second option. So to start with f of x1 equals f of x2 and see if that means that x1 and x2 have to be the same. Because then if they have to be the same, it's a function. If they don't have to be the same, then it's not. Unless it's something where you could see a counterexample right away, right? You only need one counterexample for it to fail. But with number one, that's how I started. I said, well, if f of x1 is equal to f of x2, then f of x1, if I just sub in, that's 5 times x1 plus 2. F of x2 is 5 times x2 plus 2. And then if I subtract 2 from both sides, I end up here. Divide both sides by 5, I end up here. So yeah, x1 does have to be equal to x2 here. So yes, that's going to be 1-to-1. Number two, I guess I kind of gave this away a minute ago. This is a parabola, so it's not. This is not going to be 1-to-1. If you try to do it, you say, well, if f of x1 equals f of x2, then x1 squared plus 3 equals x2 squared plus 3. But then you subtract 3 from both sides, you end up here. But if two squares are equal, that doesn't mean that x1 and x2 have to be equal, right? They could be additive inverses of each other, right? So x1 could be x2, but you could also have that x1 is negative x2. Right? Because like 6 and negative 6, you square either of those, you're going to get 36, right? It's that idea. So this one is not going to be a 1-to-1 function because x1 doesn't have to be equal to x2. It could be something else, more specifically the negation of x2. So that one's a no. If you want to do it with a counterexample, you could say, well, f of 1 and f of negative 1 here are both going to be 4. And there's a counterexample, right? You have two x values that are mapped to the same y value. So that's not a 1-to-1 function. That's another way basically to end up with that conclusion. Going down here, number 3 and number 4. Number 3, this is one where I think it's actually easier just to see it with an example. But if you think about the absolute value shape as like where the graph looks like a V shape. So you'd say, well, that's like if we took the regular absolute value function, shifted it over 4. So I just went 1 to the left and 1 to the right. So I said, okay, go 1 to the left of 4, you get 3, 1 to the right, you get 5. And then f of 3 and f of 5 both end up being 1. So there's a no, right? You got two x values mapped to the same y value. If you try to do it generally and you say, okay, well, if f of x1 equals f of x2, then these two absolute values have to be equal. But then that doesn't mean that x1 minus 4 equals x2 minus 4, because they could be negations of each other, right? They could be additive inverses and the absolute values would still end up being the same. So they don't have to be identical here, and because of that plus minus, that would throw it off. But I think this one's probably easier to see with the example. Number 4, this one does work. So if you set f of x1 equal to f of x2, then, okay, you end up here, multiply both sides by 2, you end up here where x1 cubed equals x2 cubed. But with cubes and really with odd powers, then that would force x1 to be equal to x2, so then that's a yes. So if there's anything that's automatic with where you get a yes or a no, if you have a function that's a polynomial function, like on number 4 is a polynomial, and to go back up here, so is number 1, so is number 2, if the only powers are odd, it's going to be a function. You can kind of tell, right, because number 1 just has an odd power and so does number 4. And then if the only power or powers that show up are even powers, like here with an x squared, then that's going to end up being a no. Other than that, you know, it's not quite as automatic, I guess, because it doesn't match up exactly with like being an even function versus being an odd function, right? Because this is not really an odd function, but it still ends up working out. And then this one is, and it works out. This one is even, and it doesn't work out. And I guess the even ones would not work out. That is true. But I think if you have to check and figure out if a function is 1-to-1, if it's all odd powers, it should work out. If you have even powers, either you can do this thing here or see if you can find a counterexample. And if you've got graphs, it's actually really, really simple. Just like if you have a graph and you want to see if it's a function, that's pretty simple, right? Because there you just use the vertical line test. If any vertical line intersects the graph in two different spots, it's not a function. It's kind of similar, except that it's a horizontal line this time. So if any horizontal line intersects the graph in multiple points, then that's not a one-to-one function. So like this upside down parabola here, this is not a one-to-one function. Right? That red dotted line is going to hit that parabola in two different spots. But then this thing, which is reminiscent of the graph of y equals 1 over x, that ends up being a one-to-one function because there's no horizontal line that's going to intersect that twice. Really what's going on up here on the left side and then out here on the right side is that the graph is approaching the axis. So here it's underneath and it gets closer and closer and closer but never touches it. Here it's above it, gets closer and closer and closer but never touches it. So it's not like these end up flatlining and becoming horizontal. So that does end up being a one-to-one function. For number 3, the only power that's there is an even one, so that's kind of a red flag to begin with. But if you just think about what the end behavior is like, both ends are going to point upward, right? Because that's an even power, right? And then even power in the leading term, and you have a positive coefficient of the leading term, right? Since the coefficient's 1. So the ends are both going to point up. So somewhere there's got to be a horizontal line that intersects that twice. So it's going to fail the horizontal line test. This one over here, it kind of looks like the graph of 1 over x. It's the same kind of shape. And the graph of number 2 is more or less what the graph of 1 over x looks like. It's just that 1 over x would go through the point 1, 1 and -1, -1. But it's the same general shape. So the function that's there, the 3 over x plus 2, that's a transformation of 1 over x because it's a horizontal shift, right? Horizontal shift 2 to the left, and then a vertical stretch of 3, but it's still going to be that same shape. And if it's got that same shape as number 2, and number 2 ended up being 1-to-1, then number 4 also ends up being 1-to-1. First on this page is the notation. So this f with the -1 and the superscript, that denotes inverse, and this would be read out loud typically as f inverse, rather than f to the -1 or something like that. You would call that f inverse. So here, we want to determine if f is 1-to-1, and if it is, we're going to find f inverse. Okay, well, if you look at these 4 points, all of the y coordinates are different, right? -1, or 1, -2, 5, and 0. So there's no way that you could have 2 different x values mapped to the same y value, right? Not if all the y values are different. So that should work, right? There shouldn't be any problems. It's going to be 1-to-1. And then what would f inverse look like? Well, if you're just doing ordered pairs, then you just have to interchange x and y. So like the inverse of 3, 1, 1, 3. And then an inverse of 4, -2, we get -2, 4, and so forth. So you just have to interchange the coordinates, and those would give you the points that would be part of f inverse. Then the second example is, again, using ordered pairs. Let's say we want to have a function where f inverse is not a function. You don't need anything complicated here. You just need 2 points with the same y value but with different x values. Right? So here, that's all I did. I just said, all right, well, 2, 6, 5, 6, they got the same y value and different x values, because then f inverse would be the points 6, 2, and 6, 5. So that's not going to be a function, right? If you got the same x value and 2 different y values, it's going to fail the vertical line test. If you try, I guess if you plotted those 2 points, it would. So that's really about all you would need there, is something like that. But usually the functions aren't written out with ordered pairs. Usually they're written out just in regular function notation like we've had. So if you have, f of x equals whatever, and you've got it written out as a function rather than just as a set of ordered pairs, then how do you find the equation of f inverse, right? Like, how would you do this? It seems like that must exist. Well, as long as f is 1-to-1, it does, right? So assuming that f is 1-to-1, this is what you do. Replace f of x with y just to make the solving easier. That's all this is for. then you switch x and y, just interchange where they are. So like if you have y equals 2x plus 3, then you have x equals 2y plus 3 after you do the interchange. Then you solve for y and then replace that with f inverse of x. This is much easier to see just with an actual example. So that's what we've got here. If f of x is 8 over x plus 3, here's the first step right here, just replacing f of x with y. Then switch x and y. So look at this thing. X equals 8 over y plus 3, right? Looks like this one, just the x and the y are in different spots. And then from here, you just have to solve for y. So if x is equal to 8 over y plus 3, then y plus 3 must be equal to 8 over x. Which I guess you could get that by multiplying and then dividing, but you could also just interchange them there like I did. Then if that's true, then to solve for y, you just have to subtract 3 from both sides, which is what this is here. The y equals 8 over x minus 3. And now that it's solved for y, just replace y with f inverse of x with that notation. So f inverse of x is 8 over x minus 3. Next example. So now f of x is 4 minus x over 5x. All right, well then we'll replace f of x with y. Then if you switch x and y, you end up with that x is 4 minus y over 5y. And then we got to solve for y. All right, well, I guess first clear fractions. So multiply both sides by 5y, you end up here. Then if you get everything with a y in it on the same side, so I just added y to both sides to end up here. And then you can factor a y out on the left, and you'd write that as y times the quantity 5x plus 1 equals 4. But then you could get y by itself by dividing by what's in parentheses. So if you do that, you get that y is 4 over 5x plus 1. Now we've got solve for y. So let's replace y with f inverse of x. There's the inverse. Number 3, the last one that's here. All right, well, replace f of x with y. So we got y equals 7 plus 2x cubed. And then you switch x and y, so you have x equals 7 plus 2y cubed. And then we're going to solve for y. So first get the y term by itself. So subtract 7 from both sides, you get 2y cubed equals x minus 7. And then try to get the y cubed by itself. So you divide both sides by 2 and you end up there. And then if you take the cube root of both sides, you'll get y by itself on the left. And on the right, you got the cube root of x minus 7 over 2. And then now that we've got this solved for y, we can just sub in f inverse of x notationally, right? So let's replace the y with the f inverse notation, and there's the inverse function. The next thing is graphs, where if f is 1 to 1, then if you want to get the graph of f inverse, you can get it by reflecting through the line y equals x. So what's supposed to be going on here? I guess obviously the dotted line is y equals x, right? And it's going through the origin 1, 1, 2, 2, 3, 3, 4, 4, and so forth. The blue line is supposed to be f. And then the red one is the inverse. So there are a couple of different ways that you could figure out what the inverse would have to be if you just had like f and then this dotted y equals x in there. One way is just to start with the points and just switching the coordinates. So like this point right here, that's 2, 3. So I said, all right, well, if 2, 3 is on f, then 3, 2 must be on f inverse, and that's that point right there. Or 3, 5 is on f. That's this point up here. But if 3, 5 is on f, then 5, 3, which is that one right there, has got to be on f inverse, and so forth. You can do it like that, right? 1, 1 is going to be in both, right? Because if you interchange 1 and 1, you get 1, 1 again. And then, right, that's negative 1, 0, so 0, negative 1. I guess I'm saying that backwards. There's 0, negative 1, so you end up with negative 1, 0 for the inverse function. And then you do the same thing with that point. If you're just trying to draw it correctly, there's kind of a trick to this, which is if you kind of mirror where the points are in relation to y equals x, like how this one, you go, okay, well, diagonally it's just halfway across that box. So on the other diagonal in that box, you gotta have a point in the inverse. And then here, this one, it goes across that box diagonally, like one whole box. So going right across there, you go one whole box, there's a point on the inverse. So you can do it that way too. If you're just trying to draw it, that's actually a lot faster to do it graphically rather than switching the x and y coordinates. But either way will get you to the right place. And there are a couple more examples down here. So this one's got some curvature to it, but not a ton of points. The original function, so it's still that f is the blue one and f inverse is the red one. The original function's got the origin. It's got 2, 1, and then it's got 3, 4 up there. And then it goes up like that. And then you say, well, if it goes up like that, then like here it's underneath y equals x, and then out here it's above. The inverse should be above and then underneath, and that's exactly what happens. And you could get it just from plotting the points too, right? If 2, 1 is on f, then 1, 2 is on f inverse. If 3, 4 is on f, then 4, 3 is on f inverse. And I plotted those points in there too. But if you kind of just draw in the thing that would give you symmetry about the line y equals x, you're basically going to end up in the right place. Right? So you could look at it that way too. For this one, I did plot the points, and then I just kind of drew it in saying, well, it's got to be above here and then below out here. And that's usually enough to give you a pretty good graph. Number 3 looks really complicated, but I don't know. It's repetitive, which makes it less complicated. And it sort of looks like DNA with the inverse and the original function there, right? It's that kind of helix type shape. But the original function, it's got the origin here, and then right there's 2, 1, there's 3, 3, there's 4, 5, and then same kind of things going that way. And as long as you've got y equals x in there, or you know where that is, then that should be enough to graph the inverse without too much trouble. You can do it with the points by switching the coordinates. So like if 2, 1 is on the graph of f, then 1, 2 has got to be on the graph of f inverse. And then if 4, 5 is on the graph of f, then 5, 4 has got to be on the graph of f inverse, and so forth. And here I did plot those 4 points, and then I just kind of thought, okay, well, in the 3 that are right on y equals x, so the origin, 3, 3 up there, and then -3, -3 down there, they're all going to be on it too. So I just have to plot those other points that are on the graph of f inverse, and then make sure I hit those ones that are right on y equals x, and then just kind of mimic that shape that the graph of f has, just going the opposite way, like how here f's below the line, so the inverse has got to be above the line, and then past 3, 3, f is above the line, so the inverse has got to be below the line. And you just kind of follow it along like that, and that's enough to give you a pretty decent shape. I mean, that's all that I really used here. I plotted those 4 points and then just kind of mimicked the shape of f, just going the other way around y equals x. And that's enough to give you a pretty good looking picture.